let's see the same problem and how can we do the principal component analysis using the SVD approach that we have, right? So considering that we calculated U and sigma of the matrix from the SVD, and this is something that we have already done. So let me quickly go back and consider the same example problem. And as I showed that for the data X matrix, we have computed the U and sigma matrix using support vector decomposition, right? So this, now the T matrix can be essentially written as a product of U and sigma matrix of the SVD product, right? Recall the SVD has three components, U, sigma, and V transpose. But when we are doing the transformation using the SVD, what we do is we throw away the V transpose matrix altogether and we only consider the U and the sigma matrix and the product of those two, and that gives us essentially the transformed coordinate directly. And that's the beauty of the SVD, that we do not need to solve the eigenvalue problem. We are essentially able to, to use the U and the sigma matrix from the SVD decomposition, and that gives us the T matrix directly. So if that is the case, if you look into the U and sigma calculation, this was the U matrix, and this was the sigma matrix that we have. So we will only bring those two matrices, and now we will take the multiplication of this two matrices, and if you multiply that, we will get this T matrix. Now this T matrix essentially gives the first column gives the first principal component, and the second column gives the second component that is out there. Now what I want to do is I want to quickly go back to the T computation that was done using eigenvalue decomposition process, and you will see that the T value that we arrived at that process after normalization was exactly equal to the T value that we got using the SVD process. So this is the T value that we got from SVD process. Let's quickly go back to the previous slide, right? And you can see this was the T value that we got using eigenvalue decomposition problem solving. So this T, right, the value that the matrix that you see here is exactly the same that you get after the multiplication of U and sigma matrices that is there, and that gives you exactly the same information that is there. So there are two different ways, eigen decomposition and then SVD way of solving the same problem. And again, how do we go ahead and do the dimensionality reduction, right? Now what we will do, once we get the T matrix, we will essentially throw away the second principal component, because that might not be capturing the most important information. All the information, most important information might be there only in the first principal component, so we will only keep that with us, and we throw away the second column of information. And if we follow that process, then we are able to implement the dimensionality reduction, and now we are moving away from a two-dimensional space and moving that to a single dimensional space that we might have. Okay, so if this is the original matrix X, using SVD we got T, which was this, right? This the data, single data point, there are three data points, and each data point has two different dimensions. That's why you have two columns, right? Now what we'll do, we use the SVD, we got this T matrix, we will throw away the second principal component, we will only keep the first principal component, and that is what is going to help in doing the dimensionality reduction. So this is essentially a dimensionality reduction, and we are implementing a PCA using a SVD approach that is out there. Okay, so this is how you can implement PCA using support vector decomposition method. So let's move on and discuss some of the important salient features of the principal component analysis. The singular values of the sigma matrix gives us an idea about the amount of variance of data that this principal component captures, right? And then what you can do is, using that information, you can compute what is the fraction of variance captured by the R modes. Remember, we can have the first singular value, the second singular value, third up to R singular values that are there. We can find out what is the contribution of each of the singular values or each of the mode computations we are doing, and that could be used by doing this simple computation that is there. We know the values of singular values, and we can sum up to R, and then we can sum up to K, K equal to R equal to N, K equal to 1 to R and K equal to 1 to N, and we can find this ratio, and we can use this ratio to basically find out the 90% variance, that if you are interested in capturing 90% variance, we can capture that much. If you are interested in capturing 95%, then we can find out the value of K, value of R, that capture that much of variance. So depending upon your thresholding, that if you're interested in capturing 95% of the variance, then you want to find out a value of R, or the number of principal components that I need to be taking into account. You can use this equation, and that will help you in finding out the number of dimensions that you can have in your T matrix, right? The T matrix is going to have all the different principal component, but you need to throw away some of them, right? This R value and this ratio value could be used to basically eliminate the number of columns going forward, right? And the PCA tells us which direction there is the most variance and the second most variance, and so on, as we are moving along the different columns that we have. Okay? So hopefully we covered some salient features, and again we will cover some other aspect about principal component analysis and how to choose the suitable values of R in some of the other videos going forward. So with that, I want to thank